Okay, on to the last page of questions here. So first, the short answer. Explain why the pseudo instruction LDR R0 equals 0x1234567 8 cannot be encoded as a single 32-bit instruction, and how the assembler handles this pseudo instruction. So the main reason for this is a 32-bit instruction does not have room for a 32-bit immediate. Right? And so really the thing it has is it needs things like the opcode, it needs the registers, etc. So it needs to store other stuff, right? It needs to know what R0 is. It needs to know that it is a load or a move in this case. And so it doesn't have room to put 32 bits of immediate into a 32-bit instruction. It doesn't have any way to tell the processor what to do with that 32 bits. And so that's the main reason that we can't have this type of instruction. How it handles it is it does a move W into R0 of 0x5678, and then it does a move T into R0 of 0x1234. So that's how it handles this. We just get rid of the, we split this pseudo instruction into two instructions. And really that's just important to understand that, again, you cannot fit 32 bits of immediate into a 32-bit instruction, and that this actually will turn into two instructions. So when we're counting how long something takes eventually, we will need to know that an LDR with 32 bits is actually 2 cycles instead of 1 cycle. Next up, part B, explain how FIO set and FIO clear interact with FIO pin. So this is really just from the notes and from the manual on the LPC 1768 board. Really, we just have to remember that FIO set turns on pins in FIO pin, and FIO clear turns off pins in FIO pin. That's really all we need to know for that problem. Just that set, if we put a 1 in a bit in FIO set, that turns on a pin in FIO pin. If we put a 1 in FIO clear, it turns off a pin in FIO 1 pin. So that's the only one small distinction there, is that clear, we are going to put a 1 in the bits that we want to turn off. But that's it for the short answer problems. That's really all you need to write. Let's move on to the true, false, and multiple choice. So first one, part A, how large are the instructions on the Cortex-M3 processor? Circle all that apply. This is a little bit of a trick question because we do have both 16 and 32-bit instructions in the Cortex-M3 processor. So these are the thumb instructions are 16 bits, and the ARM instructions are 32 bits. We have a 32-bit processor, so we don't have 64-bit instructions, and 8 bits is small. We don't actually have any that are just 8 bits. So this is a sort of mixed instruction set architecture, but it has these two formats. B, how large are registers on the Cortex-M3 processor? Hopefully we all know this at this point, that this is 32 bits per register, and that's evident from all of the other problems. If you're not sure, go back and use that rule that we have 4 bits per hex digit and count how many bits are in each register in the problems in the rest of the exam. C, true, false. One advantage of little endian ordering is that any sized load, e.g. 1 bytes, 2 bytes, or 4 bytes from the same address will get the same least significant bytes. So that is our fact about little endian ordering. So if we have, if we look at a previous problem and see a value from that, we can look at problem number 1 and see that we have 1100FFFF. And if we do a load from this address, the byte will take 11. A half word will take 0011, and then the full load will take FFFF0011. And that's what this is asking, is do we get the same least significant bytes? And that's the case. So since we're always loading from that base address, we can do any sized load from the same least significant bytes. So this is true. D, true, false. The instruction LSL R0 R01 multiplies the number in R0 by 2. This is, again, it's going to be true because it's just a sort of fact of how this works. Whenever we shift something by 1, Let's say we have 0, 0, 1, 1 equals 3. If we shift that by 1, that is 6. So we've multiplied by 2. Effectively, a shift is a multiply by 2 to the n, where n is the value here. So that is n. And in this case, that's a shift by 2 to the 1, or multiply by 2 to the 1, which is just 2. Part E, if x is a 16-bit number, which bit indicates whether or not x is negative? So this is, again, a little bit of a trick question. In general, when we're looking at negative, we're looking at x31 to determine if it's negative or not. But in this case, we're specifying that x is a 16-bit number. So keep in mind that you as the programmer, it's up to you to know how your code works. And in this case, if you're treating something as a 16-bit number, you would be looking at that as a 16-bit number. And then we just really need to know that a 16-bit number starts at bit 0, goes over to bit 15. So x15 would be the bit that tells us whether or not that is negative. And then finally, real quick, the bonus. So fill the blank with an instruction that will make R0 equal to 0. And it's just a blank here. You're supposed to put in a mnemonic for an assembly code instruction. And then the inputs are R0 and R0. So you're doing something with R0 to itself. You're assuming that R0 is not equal to 0 already, because that would be too easy, right? Then we just do a move or something like that. And there are multiple answers to this question. The main one that I was thinking of is exclusive OR, because exclusive ORing a value if all of the bits match, because exclusive OR has this truth table that is, 0, 0, 0, 1, 1, 0, 1, 1, right? When we exclusive OR things together, if it's both 0, it's 0. If it's 0, 1, it's 1. If it's 1, 0, it's 1. If it's 1, 1, it's 0. So if we're exclusive ORing something with itself, if the bit in the original value is a 0, it's still a 0. If the bit in the original value is a 1, because we're XORing it with itself, it's always going to be XORed with a 1, so that also turns to 0. So we actually, because we're doing it with itself, we get rid of those two middle cases, and the output is just going to be all zeros. Another way to do this is to sub or RSB. So if we've got a number, we do x minus x is equal to 0 as well. So that's another possible solution. So sub is fine. RSB is also fine. If we do the reverse sub, which is again just x minus x in a different format, that will also work properly. So those were the main answers we were looking for there. There may be some other tricky things as well that you could do, but these are the ones that will sort of work the best. So that is it for the multiple choice or short answer and the bonus. Good luck.